All right, area of a regular polygon. And so today we're going to be focusing specifically on hexagons. And that's because once you get past four sides or square, okay, the easiest one is a hexagon. And the reason why is because hexagons are made up of equilateral triangles. Okay, so it gives us, when we're finding the area of a hexagon, there's actually multiple ways of finding the pieces that we need to find. When you talk about pentagons and octagons and dodecagons and 24gons, things like that, finding the area of those are all very similar. Okay? And there's really only one or two ways to do it. Whereas with the hexagons, there's a few different ways. So we're going to talk about that today, which gives us a good introduction on how to solve the area for the others as well. Real quick recap. I'm just going to blow through a lot of these things because it's all just stuff we've done before. Regular polygon, polygon with all sides and angles congruent. Every regular polygon can be inscribed in a circle. We have not talked about this, but if we were to take every one of our regular polygons we've worked with, you can put their vertices on a circle. Okay? They all fit directly inside a circle. And the reason why this is important, I'm just going to scroll through a lot of the ones we've worked with. Square, pentagon, hexagon, octagon, 17gon. But the reason why these are important is because some of the terminology we get within our regular polygons comes from the fact that it can be inscribed in a circle. And one fact you guys can look and see is a little similarity between these polygons and circles. The more sides you get, the more it looks like a circle. There's actually a pretty good comparison from the regular polygon equation to a circle equation for area. All right, this is the diagram. You guys should have this diagram somewhere in your notes. Okay, the one on the left here. And what we're going to do is we're going to define the different parts of a regular polygon. Now, like I said, today we're going to focus on hexagons. I'm going to go through one example of a hexagon on the notes, and then I'll take one example from your homework that we'll go through together. And there are 5 total on your homework, so I'll do one with you, and you guys can do the other 4 on your own. So the center of a regular polygon is the same as the center of the circle it is inscribed in. Now, we don't draw a circle every single time we draw a regular polygon. So the center of it won't always be given to you, but you know that there is a center that does exist, okay? And that center will always be equidistant from the center to all the vertices, okay? And we call that length the radius of our regular polygon, because it's the same as the radius of the circle that would go around the polygon. Okay. So center, a radius of a regular polygon is the same as the radius of the circle it is inscribed in. And lastly is that word starts with an A, ends with an M. It's pronounced apothome. Okay. The apothome apothem of a regular polygon is a segment from the center of the polygon perpendicular to the side of a regular polygon. Okay. Now, I don't have one of these drawings peeled out, but there are some explanations of how to find the area of a regular polygon. Because what they do is they actually they draw all the radiuses. And what they do is they basically unroll the polygon so that it looks like this, okay? Where you've got, basically they take all these triangles, and what you have six, well, I only did five. Let's try six. They have six identical triangles that are all attached, okay? And what they can do is you can find the area of one of the triangles, okay? Because this apothem is the same for all six triangles. You can find the area of one triangle, and then you just multiply that times 6 to get your total area. Okay. Another way to look at it, all right, is this length from here to there. That's the same as the perimeter that goes around the entire hexagon. Okay. So what we can do, we'll come back to that question. That one. Okay, what we can do is we can, to find the area of a regular polygon, you can multiply 1/2 times the perimeter times the apothem. Now, the apothem in this case, that's the height of each triangle, because that's the distance from the center to the side of a triangle, the perpendicular, right? So if I did 1/2 times the side length, which is the base, times the height, the apothem, okay? That'd be the same with finding one triangle, but to find all of them, we can multiply times the perimeter, times the height, which is the apothem. Okay. So this is our equation. I believe it's on the formula sheet, which I shared with you guys last week as well. This is the equation we're going to use for all. Once you get past the quadrilaterals, this is the equation we use for all of them. Now, finding the perimeter and finding the apothem is the challenge. Once you know those two things, it's pretty easy to plug them in and get your area. We have to find those two things. All right, so going back here, central angle. This is another piece of a regular polygon, which we're going to need. We actually need it a little bit more when we get to the other polygons, but it's important with hexagons as well. The reason why it's not quite as important with hexagons is hexagons are nice in the fact that every one of these triangles is an equilateral triangle. Okay? These are all equilateral triangles. And the reason why I know that is because the central angle, this angle right here, we can get that by taking 360 and dividing by 6, because there's 6 of these triangles. So this angle will be 60. Okay. Well, these angles are also going to be 60. Okay. It's an equilateral triangle. And when we do the next problem, I'll explain why the fact that it's an equilateral triangle gives us some options when it comes to finding our missing parts. See people still writing, so I'll give you guys a second. All right, I got 2 more real quick facts about our apothem. Okay. So the apothem does two things within our polygon. Okay? If I had these radii here, we just talked about this being a 60-degree angle. The apothem is an angle bisector. Okay, it's an angle bisector. So it cuts this central angle in half and gives us two 30-degree angles. Sorry, those too small. Okay, these are 30-degree angles in here. They're congruent, obviously, because they're both 30. But those are 30-degree angles. The other thing the apothem does, we call this a perpendicular bisector. And what that means is that where it hits the line that it intersects with as a perpendicular, it cuts that line in half. All right. So not only does it cut these angles in half, but it also cuts the side in half. That's important because sometimes you're only going to be given a side length. And if I want to find the apothem, I'm going to need to cut that side length in half to get a right triangle to then find the apothem. Okay. All right, let's take a look at an example. All right, so here's one where we're given a radius length, okay? All we're given is a radius. Now, what's nice is when you're given a radius length in a hexagon, they also just gave you a side length. Because as I talked about before, it's an equilateral triangle, 6 equilateral triangles. Okay. Now, giving us a side length or the radius does not, that just doesn't get plugged into our equation here. It helps us find parts of it. Okay, let's plug in what we can find here. All right. If I know that the radius is 3, that means the side length is also 3. My perimeter, there's 6 sides. 6 times 3 is 18. So my perimeter is 18. So I got my perimeter. The apothem is the hard one here. Okay, I'm going to go through, because sometimes they ask you to find your answer in exact terms, like we say, give us an exact answer in simplified radical form. And sometimes they say, give us a rounded answer. If they're asking for a rounded answer, there's 3 different ways to find our apothem. I'm going to go through all 3. If they say, give us an exact answer, you've got to use simplified radical form, and you've got to use one specific way to do it. So let's do the exact answer first. Okay. What I'm going to do is I've got to find my apothem, which is this length right here. Now, when I'm drawing this on paper, I like to redraw that triangle, specifically this red one, just so there's more space. Now, we know what these angles are. Okay. We know that this angle is a 30-degree angle because we know that it was a 60 for the central angle and half of 60 is 30. That makes that angle in the bottom right a 60-degree angle. We know some lengths. We know that the radius is 3. And we know that this length down here is half of 3. I'm going to write it as a fraction. 3/2. So if I want to find my answer exact in simplified radical form, that means I have to use my special right triangles. So 30, 60, 90. A, 2A, A radical 3. Okay. So I have to use my ratios here if I want my answer as exact. Okay. So the way I would do this, I see A is 3/2. I plug that in here. I get 3/2 times radical 3. You can write your answer like that. You can write it as, you can make that radical 3/1 and then multiply across 3 radical 3/2. They're both correct. They're both equivalent. That's my apothem. Now, If I want to get my exact answer though, this is where, remember, you multiply everything except for the radical. All right, so if I take my calculator and I do 1/2, I use 0.5 when I say 1/2. 0.5 times 18 times 3, and then I'm going to divide that by 2. Well, I don't know if I'm going to divide that by 2. That's 27. So 1/2 times 18 times 3 is 27. I think we have to leave it like that, otherwise we get a decimal. Okay, that's an exact answer. Again, it's not pretty. I don't like it. Most of the time we let you guys find the area as decimals, but every once in a while we may say, give us an exact answer. Or we may say, what's the exact length of the apothem in radical form? Okay. And then you can plug that in. Like we could multiply all this out and get rounded decimal answer. Okay. So this is the way, if we need an exact answer, we would have to do it. Let's go through the other 2 ways where we can get estimated answers. Okay, we're gonna get rounded answers. All right, I'm gonna redraw my little triangle here. Where that's 3. I'm gonna leave this as a decimal this time, 1.5. How would you guys solve that? If I said, solve for that side. Yeah, we know 2 sides here. We can use the Pythagorean theorem. A squared plus b squared equals c squared. We can make xa x squared plus 1.5 squared equals 3 squared. Okay, so 3 squared minus 1.5 squared. Get the square root of that. 2.59807. Now this is why we like kind of using radicals a lot of times, because where to round. I would say round at least 2 or 3 places to start off. We'll say 2.598. So my apothem, 2.598. So if I wanted to figure that out, area equals 1/2 times 18 times 2.598. Plug that in my calculator. I get to the nearest tenth, because a lot of times you do the tenth. 23.4. About 23.4. Okay, one last way. So we did an exact way. One way we use the Pythagorean theorem. And our last one here. I'm going to redraw my triangle. All right, we were given these lengths, 3, 1.5. I'm going to write these angles in here. Last way. We know if we know an angle and we know sides, we can use trig to solve for a missing side. Okay, so let's say I use the 30-degree angle here. I want to solve for x. This angle, so opposite, hypotenuse, adjacent. So I'm going to use opposite and adjacent. I could have used hypotenuse and adjacent if I want to solve for that. Okay, could use either one. I'm going to use opposite adjacent, which is tangent. Tangent of 30 equals 1.5 over, let's see, 1.5 over x. X is low, switch, let me know. X equals 1.5 over tangent of 30. All right, 1.5 divided by tangent of 30. 2.598076. Wait a second, that's the same number I got here. Should be. We're solving for the same length. Okay. Whether we are using special right triangle ratios, Pythagorean theorem, or trig, we will get the same number. Okay. It It's just, these are gonna be decimals that go on forever, so you have to round them someplace. Okay, that's why this isn't considered exact, and these are considered rounded. Right? Make sense so far? Got the 3 different ways. Now, you're not always gonna be given, and that's why I wanna go through one more example. You're not always gonna be given a radius, okay? Sometimes you're given a side length, which is the same thing as a radius in a hexagon. But sometimes you're gonna be given the apothem, and then you've got to go and find your side length from the apothem. So that's where we're gonna start, okay? So I'm gonna go ahead and share the assignment with you guys. It's a Desmos assignment. We're gonna work on the first example together, and then I'll let you guys go from there.